All right, let's jump right into today's explainer. We are breaking down a massive breakthrough that solves, honestly, one of the biggest headaches in AI today, running out of memory. We're going to look at this revolutionary new approach from NVIDIA that completely changes how AI remembers conversations. And don't worry, we are keeping this super simple and easy to understand. No crazy jargon, just the good stuff. So, why is AI running out of memory in the first place? Well, as these large language models get smarter and process these absolutely massive documents, we're talking tens of thousands of words at once, they hit this giant hardware wall. It actually isn't about how fast they can think. It's all about how they remember things while generating a response to your prompt.
Which brings us to a really crucial concept, the KV cache, or key value cache. You can just think of this as the AI's short-term memory. You see, when an AI generates text, it does it word by word. So the KV cache acts exactly like a really diligent student taking quick notes during a lecture. Because they have those notes, they don't have to reread the entire textbook every single time the teacher asks them a question.
Imagine if, to generate the next word in a sentence, the AI had to start completely from scratch and reread everything you just typed, recomputing the math for every single word over and over. Man, that is literally exhausting for a computer and incredibly slow. The KV cache wave fixes this. It lets the AI instantly pull from its saved notes, the key and value vectors of words it already saw, so it can keep generating text at lightning speed.
But, well, here's where the headache starts. If you have a super long conversation, those notes really pile up. We're talking gigabytes of data that entirely fill up the GPU's memory. It creates a massive traffic jam. But researchers noticed a little secret. These AI nodes have what's called a low-rank structure. Now, in plain English, that just means a ton of the stored information is highly repetitive. You really don't need every single detail to get the point across.
Now, before we get to the real magic of this new software, let's look at how the industry originally tried to fix this. For a while, NVIDIA essentially took the hardware brute force approach. They just rapidly evolved their chips across 3 generations. Basically, they were trying to build a bigger and bigger room to hold all these AI nodes. First, the H100 kind of set the baseline with 80 gigabytes of memory. Then came the H200, which nearly doubled that to an absolutely massive 141 gigabytes, with bandwidth hitting a staggering 4.8 terabytes per second. And finally, the B200 arrived, literally sticking 2 massive dies together with an incomprehensible 208 billion transistors, all just to keep up. But you can't just keep building bigger, hotter hardware forever. There are physical and economic limits to that. Right, so we can't just throw bigger chips at the problem forever. And that leads us to NVIDIA's incredibly elegant software fix. It's called KV Cache Transform Coding, or KVTC. And honestly, what makes this a total game changer for enterprise users is that it is completely non-invasive. You don't even have to retrain your AI or tweak the underlying model weights to use it. It just works. To keep things simple, you can think of KVTC exactly like saving a photo as a JPEG. When you take a picture of a clear blue sky, your computer doesn't actually save the data for every single blue pixel. It just saves the main color and shape and kind of fills in the blanks later. KVTC does the exact same thing with AI memory. It drops the redundant stuff and keeps only what is truly essential. So how does this whole JPEG-style compression actually happen? Well, it breaks down into 3 really fast steps that happen right on the GPU while the AI is formulating its answer, during the inference phase as they call it. Let's walk through these steps quickly so you can see the magic. Step 1 is Principal Component Analysis, or PCA. Basically, the system quickly scans the AI's notes and finds the most critical shapes and colors of the data. It's figuring out the key components that best represent the whole picture. And the really brilliant part here, this calculation is actually done just once, offline. So applying it doesn't slow down your prompt at all. Next up, we have adaptive quantization. Imagine packing for a trip using a tiny little suitcase. You'd obviously give plenty of space to your absolute most crucial items, right? And you'd give way less space, or just entirely leave behind the stuff you don't really need. That's exactly what KVTC does with the data. It dynamically assigns lots of memory to the crucial information and gives fewer bits or just completely drops the less important stuff. And the final piece of the puzzle is entropy coding. Think of this like putting that packed suitcase into one of those vacuum-sealed bags. It acts just like a zip file on your computer, packing everything down tightly using a super fast algorithm. It all happens directly on the GPU. So when the AI actually needs its notes again, the file just unzips in the background in a flash while the AI is replying to you.
When you put all three of these steps together, the result is absolutely staggering. By applying this simple JPEG-style compression to its short-term memory, the AI's memory footprint shrinks by an astonishing 20 times. 20 times! This literally flips the entire memory bottleneck on its head.
I know what you're probably thinking. Doesn't this heavy compression make the AI forget important facts or hallucinate? Well, the researchers tested that exact thing. They ran benchmarks on heavy hitters like Llama 3 and Qwen 2.5 across complex logic and long document tests. And get this, there is consistently less than a 1% drop in accuracy. It performs practically identically to an uncompressed model. No crazy hallucinations here. And the benefits don't stop there. They actually compound. Because the data is now 20 times smaller, it completely clears out those network bandwidth jams that were choking the servers. This dramatically speeds up something called time to first token. That's just the tech term for how long it takes the AI to start typing its answer to you. And this software speeds that up by up to 8 times. To put that speed into real-world perspective for you, let's say you throw a massive 8,000 token prompt at a standard AI model on an H100 chip. It used to take a really sluggish 3 seconds just to start answering, but with this new compression instantly unzipping the cache, that delay drops to a lightning-fast 380 milliseconds. That's literally the difference between sitting there frustrated waiting for a reply versus feeling like you're having a true real-time conversation.
So, what's the big takeaway here? Why does all this matter? Well, for enterprise users, this is the ultimate tool for heavy, long-context tasks. Think of AI coding assistants that have to read your entire codebase, or autonomous agents doing complex loops. This drastically lowers those huge GPU memory costs while keeping the AI incredibly snappy. Though, quick side note, it's not really meant for super short one-off questions. The compression overhead just wouldn't make sense there.
As we start seeing AI models handling millions of tokens at once, it's pretty clear that the future isn't just about bigger hardware. It's about much smarter software. And that leaves us with a pretty fascinating thought to end today's explainer on. Just like we can't even imagine streaming Netflix today without video compression, are we looking at a future where AI memory compression is just a built-in standard for every single app we use? It certainly looks like the memory bottleneck has finally been broken.